All right, 5 minutes, just so you know, is just enough time to start getting your sourdough starter ready for feeding for the weekend. So, if you guys haven't ever made bread before, do that. It's one of those like adult skills. Get good at like 2 or 3 meals so you can impress your friends, and they're like, "Give us more," and you're like, "I'm pretty good at 2 or 3 things," but maybe you can build on that over time. So. All right, enough of that aside stuff. Let's talk about more fun stuff, more calculus. So we now have, right, so we have this like directional derivative using the gradient function. So there's that. Now, 12.7, see, we're doing like probably, hundreds of years of calculus here in a week. So, just pack it all in while you can. We want to extend this to not only, problem is when we talk about tangent lines, the answer is we can't just talk about the tangent line because there's actually tangent lines. So not only do we have slopes in every direction, which is given in this 12.6, we can therefore talk about tangent lines in any direction that we want. So first is tangent lines. If we take all these and say, let's take all these tangent lines, put them together, it turns out that we end up getting a tangent plane. So this is, and that's sort of, this should make sense because what is a tangent line do in a function? It smooths it out. It's an approximation to your function, at least locally. So, in the old day here, you've got some function, y equals f of x is moving along, and you come to a specific point, and you say, well, tell me about the function at that point. Well, it's complicated. So what I do is I just make my tangent line. So tangent line. And at least in this little region right here, in that little region there, or maybe even a little bit further, the line and the function are pretty close to each other. So if you're just doing some approximation, instead of using the function, just use the line. It's a lot easier to calculate with. Now it starts to get a little trickier before we actually do this. Look outside. I mean, everyone knows the world is round unless you're one of those people in that society. But it doesn't look round outside. It looks pretty flat. So why is that? Well, because you've basically taken a sphere, and if you're standing here, well, yeah, it's rounded, but really if it's a huge sphere, then locally it sort of looks kind of flattish. And so you're going to want to figure out what this tangent plane is. And again, it extends in just like a line in all infinitely far. This extends infinitely far. So you want to approximate, at least nearby here, that the plane is approximately your function. But now it's f of xy, so it's like a surface, a sphere, or one of these like paraboloids or these kinds of things. And also, if you have these tangent things, well, the equation of a plane, we're going to need this normal vector coming out here. So we have to figure out what that is. You've got all these tangent lines, maybe a tangent line that direction, you might have a tangent line this direction, you might have a tangent line that direction. You've got tangent lines all over the place. And whenever you do tangents, you're also going to need a normal. So you can talk about the normal line. There will be one normal line. There will be infinitely many tangents. But at least the equations, we know the equations. So let's just see if we can figure out how to put the equations in. So for a line in 3D, there's a couple ways to write it. We've got the vector form, the parametric form, the symmetric form. We're going to use the vector form on this. So a line in 3D is always the base point plus the t times whatever the direction vector is. That's kind of the most condensed way of writing it like that. So again, there you've got your line, you've got your point, you've got your direction. And what is the direction? Well, the direction is kind of like the run, the rise. You need a better one for this, but this is kind of like the in and out. It's the Z direction. Rise. We need something that's like we need a third R there. Run, rise, and I don't know. You guys can make something up. So how do I take what I just did with slopes? Because I know the slope is this duff thing. How do I get the run, rise, and the in and out off of that? So, well, again, no proof Friday here is the direction for x. So if we write this as like the direction vector for the x direction, subscripts are always dangerous because it looks like a derivative, but I don't want it to be for x direction. So this means that we won't have any rise. There will be no rise because this is in the x direction. Y is not changing at all. So you can't go up or down as far as y is concerned. So that definitely will be 0 in the middle. You know, y is constant as far as the x direction is concerned. So we just need that the run and the in and out to be exactly what the slope is that we just found. So this would be 1, and this would be the directional derivative in the I direction for f, because x and I, we're talking about the x direction, so that's the I unit vector. That will be what the direction vector is if we're trying to talk about in the x direction. What's this direction for the line? You may have also noticed, careful here, this is exactly 1, 0, whatever the x partial derivative, and that will give us exactly the direction vector for the tangent line in the x direction. So that will be the d that we use for that. Similarly, we get that the direction vector for the y direction, well, maybe this is not too surprising. X will be constant, so there will be no run in my slope or my direction vector. So it will all be in y and z. And the point is, every time y changes by 1, your z changes by whatever the y derivative is for your function. So it's the directional derivative in the j direction. Now, what about any direction? So for a general direction vector, well, it already gives us kind of like, guess what? There's the run and there's the rise. It's exactly what the direction is doing. It's the run and the rise, and now what is the z direction, or the in and out on the slope? It turns out it's exactly the directional vector, the directional derivative. So that means that the direction for u, for the u vector, will be the run, which is u1, the rise, which is u2, and then the slope will be whatever this duff is in the z direction. But don't worry, we'll do some examples here of how to get this. The point will be the same for all of them. The base point, all the lines are passing through P. So all we really need to do is figure out what the different D's are in order to figure out what our different tangent lines are. So once again, how many numbers do we have on this page? 0 and 1. All symbols. So let's do something with numbers. Okay, so for example, here's my function. Just do something small. X squared minus 2x plus y squared plus 4y. And we will look at the point 1, 2. And I think this is probably, yeah, this is going to be some kind of paraboloid. We don't necessarily need that. really think about that. So we want to find the tangent line in a specific direction. We're going to need to know fx and fy and then the gradient. So the derivative of this guy with respect to x, that's just 2x minus 2. All the other stuff is y's, and so that derivative with the x derivative will be 0. F sub y will be 2y plus 4. Again, the x parts will go away, and we'll just do y squared and 4. Okay, so if we evaluate that at the point P, then we get that f sub x will be, well, we plug in 1 for x and 2 for y. We plug in 1 for x, and we'll get 0. So there is no run to this. And f sub y will be 8. No, not 8. 2 times 2, 4, 8. That's 8. Okay, so that means that the gradient function at the point P will be 0, 8. Okay, so what's the tangent line in the x direction? So I do need to actually first need to know one more thing. I need to know what is the actual function value if I plug in 0, 2. So I need to know what the z coordinate is of my point. So technically this point, this 1, 2, is not the point on the line. It's the point xy. Now I figure out what the z is. So the z will be the function at the point 1, 2. So I got to plug in 1, 1, 2 here. And what do you get? And you plug in 1 for x and 2 for y. So we get 1 minus 2 plus 4 plus 8, 12 minus, so that's 11. So that means the z coordinate is 11. So when I try to figure out my tangent lines, then we'll actually do 3 of them. I haven't given you what the u direction is, but if I look for the x direction, then the line will be 1, 2, 11. That's my point. And t times the direction vector for x. So on the previous slide, the direction vector for x was 1, 0, and then whatever the derivative for f is in the x direction. So it'll be 1, 0, and then 0. That's the f sub x point, f sub x value at the point. So you could, I guess you could combine that into 1 plus t and then 2 and 11. So, you know, it's only changing in the x direction. If you said for y or in the j direction, that would be the tangent line would be the same point because you're still going through the base point 1, 2, 11. But now, what's the slope there? Well, according to the formula, it's 0, 1. Again, on the last slide, 0, 1, and then you do the y derivative, which is 8. If I gave you one more, so for example, suppose that if I tried to do the u direction, which was northeast, let's go northeast, so that would be 1 over square root 2, 1 over square root 2. So over 1, up 1, but you got to make it a unit vector. And that tangent line would look like 1, 2, 11. And then I have to go t, and what goes in there is u sub 1, so that's 1 over square root 2, u sub 2, that's 1 over square root 2, and then this last part has to be the directional derivative at u. So I'm going to have to take the gradient and I'm going to have to dot it with u. So what do I get if I take the dot product of 0, 8 dotted with 1 over square root 2, 1 over square root 2? Well, do the dot product. First component's multiplied, second component's multiplied. The first component's multiplied is 0, so I just get 8 divided by the square root of 2. And that will be my in and out for the z. So run, rise, and in out. And those will be three possible tangent lines. You can get infinitely many by just doing this last one and then changing the u vector to be whatever you need it to be for a specific problem. Okay. Well, let me at least finish it off with the equation of the tangent plane here. I know it's kind of a lot for the morning, and we can review more stuff on Monday. We should start working through homework problems. Is again, if we want to have our little surface, suppose it's a sphere, we can talk about a tangent line in one direction, talk about a tangent line in another direction, talk about a tangent line and then tangent line, and then tangent line, and tangent line. And if we put all these tangent lines together, they together will end up forming the tangent plane. So it's like the collection of all of these tangent lines will give me the tangent. So what's the equation of a plane? So you got to go back and you're like, hey, what's the equation of a plane? It's like a times x minus the x coordinate plus b times y minus the y coordinate plus. So we're going to have all the components here together, so we'll be in good shape. C times z minus the z coordinate equals 0. So that's the standard equation of a plane, where x naught, y naught, z naught is my base point. So is my point. And the vector ABC is the normal. And so that one points, I think we're getting too close here, but it points perpendicular to the plane, so coming out of the plane. So the only thing I need to do, I know the point, I already got that from my previous problems. How do I find the normal? And this really brings a lot of this stuff all together, that if you wanted to know the normal, it's a thing that points perpendicular. How do you create things that point perpendicular if you know things that are down below? And the answer is, I'm going to do a cross product of two specific vectors. But the idea in your head is like, I need to construct something that's perpendicular. The best way to do that is to take the cross product of two things, and I will get, by the right-hand rule, my thumb is the thing that's pointing as the cross product of my two things. So it turns out nicely that the normal is just the cross product of the direction vector for x crossed with the direction vector for y. Yay! And that sort of makes sense, because it's like the direction for a line in the x direction, the direction for the line in the y direction, both of those are in the plane. So if I cross them, they will be perpendicular to the plane. And so I will get this. I already know dx, I already know dy, I know the point, and all I got to do is cross them in order to get the answer. So the shortcut, what happens if we actually work this out? So dx, again, is the vector 1, 0, and then the partial derivative of the function. And I cross this with 0, 1, the partial derivative with respect to y. So if we make our little ijk here, so you can either figure it out and cross them, or we're going to get a little formula for it right here. So not only is, I guess, no proof Friday, it's all formula Friday. So you put in, what am I doing? I'm giving you the answer before I put anything in. Okay, so I put in the vectors 0, 1, fx, and 1, 0, fx, and 0, 1, fy. So we got to work this out doing the cross product of that. So how do you do the cross product? So we cross out I, we get this little subdeterminant down here, 0 times fy, 1 times fx, and I subtract. So that'll be negative whatever the f derivative is, or the x derivative is. How about for j? Okay, so j has a built-in minus into the formula, and I do 1 times fy and 0 times fx. So 1 times fy, I just get fy, it has a built-in minus, so I'll get negative the derivative for y in the y direction. And then how about for z? This is even easier. I just cross out these two things. I get 1, 0, 0, 1. I got to take the determinant of that. If you took Math 103, that's called the identity matrix, and the determinant of that is just 1. And so that exactly right there is the formula for the normal. I just write it out in the next thing, put it in the box here. We don't have to do any cross products. We've done all the work. That's exactly the normal, and that will give me my A, B, and C that I can plug into the tangent plane. And I can also create the normal line by using that as the direction vector for the normal line. So if you followed all that, then back in the example, so fx, y, in the last example, x squared plus y squared, no, sorry, x squared minus 2x plus y squared plus 4y. He said at the point where x was 1 and y was 2, then we ended up getting that if x is 1, y is 2, z would be 11. So I would get my point 1, 2, 11. So I have my point. Now in the formula, I need to know what the normal is. So I just recall it here. You see the normal. I just told you it's the negative x derivative, the negative y derivative, and 1. So that was my previous slide. So recalling that fx, and again, you can just look back at the slide, I guess, but the derivative is 2x minus 2 and 2y plus 4. If I stick this where x is 1 and y is 2 to get to the specific point that I'm interested in, then the x derivative will be 0 and the y derivative is 8. And so now I have all of my pieces. The normal is negative 0 or just 0, negative 8, and 1. And now I've got my point and I've got my normal, and I can create both the normal line as just using this as the direction. So it's just 1, 2, 11 plus t times 0 minus 8, 1. And that's the line, at least in vector form. And then we get the tangent plane by doing 0 times x minus 1 plus, well, it's negative 8 y minus 2, and then plus 1 times z minus 11 equals 0. So again, just pulling out the 0 minus 8, 1 from the normal vector, the 1, 2, 11 from the point, and I get my normal line and my tangent plane. I've also got my 3 tangent lines. I know that I'm talking about the gradient to get this stuff. The normal is the cross product of all of this, so it really does tie in quite a lot together. We're getting near the end of the chapter, so we might as well tie everything together. The final section of that is trying to find maxes and mins. So remember the end of Calc 1, how do you do max mins? Well, If you don't remember, we'll dust the rust off there and do some of that stuff. So it's quite a lot in one morning. It does take a lot of practice to go through and work out some of these problems to get the full sort of understanding. But at least it's not something too radically new. I mean, it's lines and planes, so we need points and directions to get them from, in this case, slopes, which are the partial derivatives. Anyway, that's enough of me talking. So let's see if you got any homework questions. Cue, cue the cricket noises, huh? No questions on homework?
Sure, I think I have a question.
Yeah.
So I'm pretty sure I got like the answers, but it was just based off of like comparison to other problems in the notes for
Okay.
12.2.
Yeah.
I just I really don't understand what this open, closed, and unbounded stuff is.
What it means in the
Yeah.
grander sense is a very abstract definition of what it actually means to be a limit. We need we need it. As far as a deeper understanding for this class, it's not going to be so crucial. The point is if you can draw a region that is something like this, and you're talking about the region, and I draw a solid line to mean that I include that in my set, then this set is called closed, just because it contains the boundary. Boundary. And it is bounded because I mean, it really means bounded in the sense of the English word. It's like enclosed, and it doesn't like explode out. I can draw a fence all the way around it, like I can get a finite amount of fencing and fence it in, and that's called bounded. If the edge is not included, I'm going to draw an afterthought here. And I only talk about the stuff strictly inside, but not the fence itself, then it is just called open because it doesn't contain the boundary. But it's still a bounded set because if I wanted to, I could enclose it with a finite amount of fencing, or I even could just like put a big circle around it. If you can draw a circle around your region, then it's bounded. It's not getting too big. So there's that. Now, how do you get something that's not bounded? Well, you could just say this. What happens if I drew like a strip like this? So here's the XY axis. And I said, I want everything between 0 and 1 for Y, all the way out, like this. So this one is definitely unbounded because you can't draw a circle around it. It keeps going over and over and over and over and over. So this is unbounded. But at the same time, it's actually, the weird part is closed, is all the part you can see, like as far as you can go, every time you go, it does contain the boundary. I can put fencing, it's infinite fencing, but it does contain the boundary. Anytime you have a dotted line, that means it doesn't include, it does not include, and then that would be called an open set. If it does include the boundary, it's called a closed set. If it stretches off to infinity, it's called unbounded. If it doesn't, then it's called bounded. And really, that's the only sort of important part for this. That's the short answer.
Thank you, sir.
So open and closed it's like infinite versus finite.
That would be the bounded part. Open closed is whether it contains the edge or not. If I said something like this, here's my set. Take the set of all points such that x squared plus y squared is strictly less than 1. Strictly less than 1. So what that is it's a circle, not including the circle, but it's including every point in the circle. That's called an open set because the boundary points are where x plus y equals 1, and they're not in it. If I instead said, let's take the set xy where x plus y is less than or equal to 1, that would be the full circle, including the boundary, and that would be called closed. So open closed is just the boundary. Is the boundary included or not? Unbounded bounded is, does the region sort of shoot off to infinity or not? Clear as mud.
Sir, how would you graph the set that has xy that y does not equal x squared?
Okay, so think about it, it's like how many points in the plane have the condition that if you square x, you don't get y? And the answer is a lot. You know that every point down here in the bottom, that's negative y. So can you find a point, down here, if I pick this point down here, say 1 minus 1. Okay, so there's x and there's y. What happens when I square x? X squared is 1. Is that equal to y? And the answer is no, and therefore that point would be included because you just throw in every single point that when you square x, you don't get y. It looks strange, but that's it. So on the opposite, it's like, wait a second, which points do I actually have where y is x squared? So look at that first, and then throw those out is basically the idea. So where's the set of points where y and x are the same? Well, what does y equal x squared look like in a graph? I mean, that looks like, it's a parabola. That's what that is. And this is the thing in your head, eventually it's like, you see a picture and you see an equation, they are representatives of the same thing. All the points on this graph are points, coordinates, so that if you squared the x, you would get the y. And that's why the point 416 works, because you square 4 and you get 16, and therefore that is satisfied. This is every single other point, like it's a lot, that doesn't fall on that parabola. So if I drew the parabola with a dotted line, then any point above it and any point below it would work. All of those points would satisfy this thing here. So that's it. I mean, it's a lot. It's almost all of the plane. Because what are you taking away? You're taking away like a one-dimensional object. You barely even notice it. So that's it. That's what it is. Now, the boundary of this is the parabola. It's kind of like the edge. And I know it's like the boundary, that looks a little weird, but instead of boundary, maybe I think it's like the edge of the region. The edge is the parabola. Is it included? And the answer is no. So if it's not included, then that's called an open set. Is the shaded part bounded? No, it's almost the entire plane. So it stretches off to infinity and bounded in almost every direction. So this is an open, unbounded set. And that's it.
Thank you, sir.
I don't want to get, it can't get more complicated. Like, what happens if I wanted the left half of the region, but not the right half, and I do that? What kind of set is that? You're like, well, it's bounded, but is it open? No, because it includes part of the boundary, so it's not really open. Is it closed? No, because it doesn't include all the boundaries. Now we have a set that's bounded, but not open and not closed either. And I think it's actually not a joke that they actually call it cloaking. So it's like partially closed, partially open. And these are just like, come on, those are awful. All right, any other like homework or even just concept questions that are still like nagging at your brain?
Sir, can you go over problem 32 for 12.3?
32. All right, so now we've got a function that has 3 independent variables, and so it's like a 4D kind of thing. It's got X, Y, and Z in there. And really you can think of maybe this is like another variable. Sometimes they're like, crap, we ran out of the alphabet, so we'll just jump back to W. So you want to find the derivative of this guy now. You've got an X derivative, you've got a Y derivative, but you also have a Z derivative. And now in this case, when you go on the X derivative, you think of Y and Z as constant. Because on an X derivative, only X is changing. So that means the rest is like held fixed. So this guy right here, maybe not too surprising, will be 3x squared y squared. It's like a constant multiple times the derivative of the x. Second is very similar, 3x squared z. But the last one has no x's in it at all, and so that derivative as far as x is concerned is 0. And then you just repeat it on these other two. So x cubed is considered positive constant, and so you multiply by 2y. The second term has no y, so that's 0. And the last one is 2yz. And then the same thing for z. This has no z's in it, so if that constant is 0 derivative, then we have x cubed, and then we have y squared. Yeah, those are just multiples of z. So those are the x, y, and z. First, that's like the first partial derivative for the first partial. And now the book says, find a bunch of these, find some of the mixed ones. So basically off of each of these, you could do x derivative, y derivative, z derivative, the second partial. And then same thing here, you can go x, y, and z. And just for emphasis, this would be the fxx derivative, like I went x and x. This one, just to make sure you got the notation, is x first and then y. So on the subscripts, you might even want to put a parenthesis in there. I do fx to get to here, and then I do y. And then eventually they just drop the parenthesis at y. So there'll be fxy, this will be fxz. The ones in the middle will be fyx, fyy, and fyz, because they're all fy's and then x, y, and z. And the same thing with here will be x, y, and z. And we'll get fzx, fzy, and fzz. And in the particular homework, it says to find a couple of these. Well, it said find these first three, and then like f, y, z. So that one there says do y first, and now you're here, and now do a z derivative on top of that. So to do a z derivative, that's going to be gone because it's considered a constant for z. So we just get 2y. And then the other one says do zy. So we do z to get to here, and then we do y from there. And so x is constant as far as y is concerned. We get 2y, and they actually end up being the same. And I think that this is something that we said maybe in passing, or maybe we guessed it. But yeah, it turns out that if you do a derivative of two variables, or the second partial derivative that's mixed this way, it's the same thing if you go the other direction. In this case, you've got a bunch of them. If you went yx, that should be the same thing as xy. If you do xz, that one should be the same thing as dx. We've already seen that yz and zy are the same. And then you'll have these other three, x-axis, xy, or x, y, and z. Is that okay?
Yes, sir. Thank you.
Any others? Anyone? Okay, well, I think we're kind of caught up in the schedule, so check the homework for Monday. I think that we do have our next test on Tuesday. And that, I think, stops at the last section, 12.5. We can check that. But on Monday, we will talk about homework. I think we talk about extreme values. So let's finish off chapter 12. Do a little bit of reviewing for the test on Tuesday. We can talk about whether we want to do the test in the morning or in the afternoon. I don't have a preference. And otherwise, I'll try and get caught up on all the homework. Some of you are turning in some late homeworks, which is good. If you want to get those in, so you know the stuff and it doesn't cream your grade. For those of you who have been working diligently, good job. I'll keep track of that. Maybe I'll give you a little kudos at the end. But catching up is important too. So if you have questions over the weekend, just send me an email, send me a text or something. Otherwise, enjoy your weekend.
Thank you, sir.
Yeah.
Thanks, sir.
Have a good weekend, sir.